The first presentation this afternoon is Chris Gammon's. Chris has been coming here not as long as I have, but almost as long. He's a professor up at Montana Tech. He's somebody that I've relied on for help with geochemistry and things like that for years. He's going to talk about recent changes to the pH and chemistry of the Berkeley Pit Lake. It's all yours.
Thanks, Dave. So, yeah, I've been in Butte since '97 and kind of been watching the progress of the Berkeley Pit as it's filled up and also changed its chemistry. So, two pictures. One on the left was a traditional old-timey Berkeley Pit Lake with its characteristic deep red or almost black color. And on the right is how it looks now. So what's happened? So my outline here, look at some trends in the pit lake chemistry. And the period of interest is really going all the way back to 2005 to the present. And then those changes, to understand those changes, we have to know how the pit changes to how the pit has been managed. And we'll talk about the vertical structure of the lake, whether it's been meromictic or vertically mixed, the geochemical processes, and possible future trends. I don't really need to go through the fun facts, but maybe call your attention to here at the bottom. I want to just point out that the pit lake is a terminal lake, meaning there's no outlet, and it has a lot of water in it, 200 billion liters. And the other thing I wanted to point out is that the increase in elevation has stabilized so that it's not gaining volume anymore. And we'll see why in a minute. Also, sources of info. So later, I think these slides are made available. But good sources of info, both for the layperson, the actual raw data. And by the way, almost all the data I'm showing today was collected by the Bureau of Mines and Geology in Butte. And then some journal articles that I've been involved with. And most of today's talk actually is taken from this first journal paper, by myself and Gary Iacopini. All right, so Berkeley Pit, we always thought of it as having a pH around 2.6, and what's shown here, a series of slides where we have the surface water in the black triangles, and then the deep lake sort of below the chemocline that comes and goes in the open squares. But basically, pH 2.5 during most of its history, and how we know that is people in the Bureau would go out in this little boat someplace in the middle of the lake and then drop data sondes and collect their samples. But then there was a bad landslide, and it caused people to think it was too dangerous to go out put a person in a boat anymore. And so we had a data gap, and it wasn't until the remote control boat was built and tested that we could get data again. And look at the pH had jumped all the way up to the mid threes. And at first, I was, not involved with getting the data. I thought, it must be bad pH calibration or something. But lo and behold, it just continued to rise to where it is now, poised around 4. So I was surprised. A lot of people were surprised at that. The other thing that was happening during all these years, the old Berkeley Pit Lake had like 1,000 parts per million of iron in it, dissolved iron. That's why the color was so vividly red. And there were differences between the shallow lake and the deep lake, which I won't go into. But if you take a weighted average of the iron concentration for the whole lake, and then you can see how it steadily decreased during all these years, 2005 to 2010, to the landslide that happened, I don't remember which year that was, 2013. then again, a data gap, and when we got back to monitoring and collecting samples, really almost no iron left in the lake. So where to go? We estimate over 400 million pounds of iron-rich sediment precipitated out of the water column and settled to the bottom of the lake. And we also think that most of that iron precipitated as this mineral here, schwartmanite, which is this fluffy sort of pincushion thing under a scanning electron microscope. It's metastable, and that's potentially important, which I'll get to in a minute. There's also some jarosite coming out of the water, but mostly schwartmanite. Enough that it would fill an Emhoff cone. This is Nick Tucci's photo, but Nick would put out these Emhoff cones from the boat, and they would just fill with sediment in a couple months. Okay, so what caused all these changes? And there's two main things. The copper recovery project, number one, I'll talk about, and number two, the effect of disposal of lime treatment sludge into the lake. So, the copper recovery, most of you probably haven't seen this, but excuse me, I'm reacting to my Pepsi. But they just, you take water, say Berkeley Pit water, and you pour it over scrap iron, and in maybe 4 or 5 hours of contact time, most of the dissolved copper will plate out on the scrap iron as elemental copper, and the reaction's shown here. It's an electron exchange reaction, and it works. And so, the mine was doing this. They basically were mining copper out of the water of the Berkeley Pit Lake for many years. And this is just an example of some of the copper sand after the scrap iron basically disintegrates to this copper sand. And then there's aluminum can that's an impurity. You can see the same reaction in some of the underground workings in Butte, where the mine water's plating old steel rails with copper. So the thing that's important here is they did a lot of this. So now I'm going to show, this is sort of a cheesy cartoon map of the area to see how the water's been going and the changes and so forth. But here's the Berkeley Pit sitting here, and a lot of people forget, but there is something roughly like 10 million liters per day of groundwater coming into the Berkeley Pit, and there still is, from the natural groundwater entering the pit as well as the flooded underground mines. All right, but then here's this copper recovery circuit, and just look at that number. So 50 million liters per day, roughly, would be cycled from the lake to the precip plant and then back to the lake. And the effect was huge. Now, as I go through the rest of this, a couple other features. There's the large tailings impoundment to the north. There's so-called Horseshoe Bend Springs that are collected. These used to be collected and lime treated, and then that water was reused by the mill and back to the tailings impoundment. But that last little thing that just popped up is the lime treatment sludge. And the volume is very small, but it's 24/7. It's a small stream of water and suspended solids that's going into the lake 24/7 since basically 2003. What else is popping up? Oh yeah, in 15 years, roughly 1.3 lake volumes was passed through the copper precip plant. So that has changed the limnology of the lake. Okay, the second thing, the lime treatment sludge disposal. Although it's a small volume, it's had important effects. So from 2003 to 2018, it was treated Horseshoe Bend spring water that was treated with lime, and then the high density sludge was returned to the lake. And that sludge has alkalinity, roughly 1 equivalent per liter of alkalinity, which is sort of like you're titrating, a cup of acid with a base and just slowly adding that alkalinity. So the discharge rate was small, but had that big effect. And I should say that most of the alkalinity in the sludge is in the mineral particles, the solids, not the water itself. The water itself doesn't have very much buffering ability. All right. Oh, and these are some of the hydroxide minerals. So magnesium, zinc, aluminum, iron hydroxide, etc. Now, because I'm a professor, you know, I have somewhere in my lab some Berkeley Pit water from way back, and we do these in-class demonstrations, and I could set up a titration experiment and add a little bit of base and measure the pH and so on. And excuse me, by the end of the period, we'd have a titration curve. Looks something like this. So this is as the base is being added here, and this is how the pH is changing, starting at 2.5. And as you'd expect from chemistry, when you get to about 3 pH, you have to add a lot of base to see increase in pH. Well, what's happening? The iron is precipitating out. So we have an iron buffer. The dissolved ferric iron is precipitating out, probably as Schwartmanite. Then once all the iron's gone, boom, pH rises quickly up to the next pH buffer, which happens to be aluminum in the case of the Berkeley Pit. And so aluminum would start to come out. And the whole time the students are going, wow, that's cool. I mean, you see the red stuff, and then as the white aluminum comes out, it turns brown. And then when all the aluminum's gone, then the pH would rise on up, and probably some other reactions happening up there. So the same thing's kind of happening on a much bigger scale out there. And I like these two photos, because the one on the left shows the difference in scale of the, this is the copper recovery, this cycle right here, taking it from the Berkeley Pit to the precip plant and back, a very large waterfall, and this is the sludge returning to the pit. But from an aerial view, on the right side, you see that the precip plant water enters into the lake with no reaction. It just goes back into it, where the sludge volume produces this huge plume of precipitates as the alkaline sludge mixes with the pH water, low pH water. Did I just use? No, okay. Don't have time to go through this whole thing, but I wanted to point out one important thing. That the water that was pumped for the precip plant had to be, the intake pipe had to be below the chemocline that separated the shallow water that already been, the copper already been cemented out, from the deeper water that had more copper. So you're taking deep water, cementing the copper out, and then returning it to the surface of the lake. So overall, you just did this with a lake. Skip all that. And then these are from kind of old slides, but timeline on the bottom, and this drawdown here, that curve, is the depth, in this case in meters, of the interface between the shallow, what we call the the mixolimnion, and then the deeper monomolimnion, or the water that never mixes with the shallow water. So that interface, because of the copper precip cycling, was drawn down. Each year it would drop, 5, 10 more meters. And then by 2009 or so, it hit the bottom, and the lake ceased to be stratified from that moment to the present day, really. Anytime people have gone out with their probes and such, there really isn't any strong vertical, you get some seasonal temperature variations, but not a strong chemocline. All right, now let's look at here. There are some comparisons for data from the early days, 2003, 2011 are in yellow and red, and then the later days in green and blue. And so we see, this is depth on the left. So we see, of course, pH was around 2.5 in the old pit and is now poised around 4. The middle one shows a slight improvement in specific conductance. So there's less total dissolved solids in the lake now than there used to be. And then the last one, which blows my mind, is there's dissolved oxygen in the pit lake now, where there used to never be dissolved oxygen below maybe 5 or 10 meters. Now there is, all the way to the bottom of the lake. And so that's amazing. I'm going to go quickly through these because of time, but the upper left. So what's shown here are a series of depth versus concentration plots. And as I go, if you follow my cursor from the right to the left, that's marching towards the present day. So showing iron concentrations, say back in the early days, over 1,000 ppm, marching across, and you can see that drawdown in the chemocline, marching across to where it is now, essentially near 1. And we can explain these various things. So we know that the iron had precipitated out of the water. We know that copper, for example, has decreased over time. Well, that makes sense because they've been doing the copper precip. Notice, though, it doesn't go to 0. Like, it seems some water rock interaction is causing the copper concentrations to want to sit right around 60 parts per million, which, by the way, is still quite a bit, and it can be precipitated out of the water. So aluminum has actually increased in concentration, probably due to redissolving of some of those sludge particles, and zinc has done nothing. So just an example of an element that really hasn't reacted yet. The top one, magnesium and sulfate, we've seen some changes that we think we can explain basically from sludge, precipitation of gypsum, and other effects. And then on the bottom, kind of interesting here, is showing arsenic and phosphorus. So the geochemists know arsenate and phosphate, very similar in chemistry. They both love to adsorb onto iron oxides. And so over time, arsenic and phosphorus were stripped out of the water column by all that Schwartmanite that precipitated out. So the lake is now pretty much, what's the word, oligotrophic. It has almost no, well, we can't measure any nitrogen in it, and it has very, very low phosphorus. All right, now here's the part that was kind of scratching our heads about for a while, and that is that the total acidity of the lake. So if you're not familiar with that term, acidity is it's a capacitance measurement anyway, so it's the sum of all this stuff. So if you were going to treat Berkeley Pit water, you'd have to add enough lime to take down the protons plus all of these dissolved metals, the iron, the copper, the manganese, the zinc, so on. And actually it turns out most of the acidity in the Berkeley Pit Lake is in these dissolved metals, not in the protons. But so the Berkeley Pit acidity has been was slowly decreasing. They're in the landslide data gap, and it's like leveled off. It's interesting to look at how that acidity breaks down in the old lake from, say, 2005 or something. Almost half of the acidity was dissolved iron, but today over half is aluminum because there's almost no iron left. All right, now, so the big question is, if that sludge is still going into the lake, how come the pH is leveled off, and how come the acidity has leveled off? How come we don't see it continuing to get better? And so one idea is that we hit that aluminum buffer. However, if you look at aluminum concentrations over time, well, you might argue that there's a slight decrease in the last 5 years, but bear in mind there's some uncertainty and whatnot. I don't really see, we don't see a lot of aluminum coming out of the lake. If you put Imhoff cones out in the lake today, they don't fill up with aluminum precipitates. So I don't think that's the answer. So I think there's another reason, and that is mineral transformation. So if you do a titration in a lab with Berkeley Pit water, you get some results and you go, ah, that's cool. But that titration isn't really mimicking the real life because you're not looking at what's on the walls of the lake and the sediment that's on those walls. And it turns out, and this is something I didn't realize until a year or so ago, that Schwartmanite, being metastable, wants to convert into a stable phase like goethite. But the kinetics are really, really super slow at a pH of 2.5. But at a pH of 4, the rate is faster, and people have done the experiments in the lab. And so as the pH is increased, I believe, and Jim Jonas is working with me on this to try to quantify it, but we think that these metastable phases like Schwartmanite and jarosite are slowly converting back into goethite, releasing protons, which is causing the pH to kind of stay put. And if you understand that, that's the hardest thing to understand in this talk. So here's the Berkeley Pit circa 2022. We've got, well, it's kind of a green color now. Don't forget that all those billions of pounds of iron precipitates, not just at the bottom, but on all the benches, and I've, of course, exaggerated scale. And we still have a pump taking water up to the to go through the copper precip plant and the lime treatment, but there's some differences, and I'll show you in the next. The lime treatment sludge is still going back in. As that lime treatment sludge goes back into the lake, the aluminum hydroxide and the magnesium hydroxide particles redissolve into the lake, releasing their OH, their alkalinity. And however, that's balanced by the fact that the pH is higher now, is allowing the Schwartmanite mineral to sort of go through diagenesis a little bit faster to form goethite. And I guess, maybe, hypothesis, is that these protons that forming from this are balancing out the OH from the sludge. Therefore, the pH of the lake is just sort of sitting there. That's not for sure, but professors like to put out ideas. So here's the Berkeley Pit, circa 2022. I was just talking with Mark Thompson, and it's not quite exactly like this. There's some other wrinkles, but more or less. We still have that groundwater coming in, unseen. We're still pumping Berkeley Pit water up to the copper precip plant, but big difference is now the water isn't going back. The water that's pumped out of the Berkeley Pit is not going back into the lake. It's now going over to the lime plant, to the mill, up to the tailings pond. So basically this is allowing the Berkeley Pit to not rise anymore. So they're pumping enough water to offset the water that's coming in as groundwater. And so, well, I apologize. Oh, where are we? Mill. Tailings pond, pH 10. Then we can't keep pumping all that water up to the tailings pond. So you got to decant water from the far northeast side of the tailings pond, put that through a polishing pond, a new polishing plant that Wood built down along Harrison, and then discharge that water to Silverbow Creek. So if you didn't know, for the last more than maybe 2 years, water that started in the Berkeley Pit Lake on its long, tortuous path is now being discharged to Silverbow Creek. So that's gone on. Now, and there's that sludge still going in 24/7 from the lime plant. Now I'm almost done, so what lies ahead? Pumping and lime treatment is going to happen for a long time of the Berkeley Pit Lake. But the Pit Lake surface elevation is no longer rising because they have the technology to treat that water and release it to Silverbow Creek. And meanwhile, sludge will continue to be disposed of into the lake. So this means eventually we'll see a lot of aluminum solids start to precipitate out of the lake. Maybe it'll change color to more like clam chowder. I don't know. But and we'll see the rise in pH through the 4s. And meanwhile, though, we don't think the concentrations of copper, zinc, and cadmium, which are lethal to the waterfowl and such, are going to decrease in the foreseeable future. But in the long term, they will decrease. And I don't have a pop-up, but I almost think that I want to say, that the Berkeley Pit is not too big of a problem to fix, which I wouldn't have realized that when I first saw it. I thought, oh my God, but now seeing all the iron come out of it and the pH rise as much as it has, and maybe understanding it a little bit better, you can see the path forward that it will eventually get up into the 5s. Okay, so that's it. I'd like to thank the Bureau, of course, and also MR, BP, ARCO, and the state DEQ. Thank you.
If the copper recovery project reintroduces dissolved iron to the water, to the lake, as it looks like it does, how do you explain the production actually of iron?
Right. So the two things that was happening. So by pumping deep water to the surface and then cascading down that waterfall back to the lake, it all got oxidized. So ferrous went to ferric. And ferric is less soluble than ferrous, and so these ferric compounds would precipitate. And but if that was the only thing happening, the pH never would have risen out of the 2s. You needed the sludge to continually add the alkalinity to raise the pH to keep it going until eventually all of the iron is gone. And it's not all gone. It's like 1 ppm. Yes?
Hey, Chris. Are you able to work on the biology aspects of the problem?
No, I don't know anything about biology. I think there's been, I think some people have collected samples. I know that the University of Montana, they collected some samples and they were unimpressed with the dominant microbes were what you'd expect, the sulfur bacteria and iron bacteria, and it never even got published. So, but meanwhile, you have people like Don and Andrea Sturley who are finding really exotic chemical compounds that they're being able to isolate and finding medicinal, like cures for cancer and such.
Sure. I'm just thinking of kinetics in the system.
Oh yeah.
Various solubility constraints. If you want to lose copper, lead, and zinc, sulfide would be a great mechanism.
Oh yeah, that's totally true. And now that yeah, thanks for bringing that up. Now that the pH is rising, you're getting into that window where maybe sulfate reduction could happen. Right. Yeah, it'd be really good. And Jim, working with, I forget his name, he just gave a talk with the drones. Sorry, thank you. They have the technology to collect core samples, sediment samples, not from the bottom of the lake maybe, but from those benches, and then see how they change over time. Yeah, it's all a moving target.
But could really fill in some pieces of the puzzle.
Thanks. I agree. It's important. Yep. So sulfate's complicated because there's a lot of gypsum that is in the pit sediment. And actually, some recent Imhoff cones that were recovered were predominantly gypsum. So sulfate can't really accumulate. Man, that Pepsi's really getting me here. Can't really accumulate because it just, boom, comes out as gypsum. I think that's the control there. Yeah.
Thanks, Chris.
Okay, thank you.